sac223 problem number 3 wants to know, how thick must the N1 equal 1.21 anti-reflective coating on an N2 equal 1.46 glass lens be in order to minimize the reflection of normally incident light of wavelength 550 nanometers? Okay, we're going to assume this lens is going to be used in air, and let's put call it N0, index of refraction of the air, which 3 sig figs is 1.00. Then we got our thin film with index of refraction N1, and the glass back here with an index of refraction of 1.46, the N2. I think I'll write N2 and N1 in here. Alright, now we got some light coming in. I call it almost normal incidence, but not quite, just so we can see the reflection. And we got light bouncing off of that surface, and some of it goes right through, bounces off of that surface. And to minimize the reflection, we want the light that reflects off of here to interfere with the light that reflects off of here destructively. In order for that to happen, we need this path difference. Let's see, this path difference. This one travels this much plus that much further, approximately 2 times the thickness of our coating farther. So the path difference is about 2t if the thickness is t, and we want 2t to be equal to a half a wavelength. That way, for instance, the crest of one wave would be interfering with the trough of the wave, the next wave. I'm going to call this lambda 1, representing the wavelength of the light when it's in this material 1. Remember, it does change. It's got a wavelength lambda out here, which will be the 550 nanometers. And a different wavelength in here, which I'm calling lambda 1. I need one more consideration. This is accurate if there's no phase reversal, or if you get phase reversal at both surfaces. We're going from a lower index of refraction bouncing off of material with a higher index of refraction, so we'll get phase reversal right here. A crest coming in would immediately be a trough on the way out, but we've also got phase reversal here because N1 is 1.21, and in fact that's the only reason we needed to know what this material was, just to know that N2 is greater than N1. So again, we're in the material with a smaller index of refraction. You bounce off this interface between that and a material with bigger index of refraction. You get phase reversal. So we get phase reversal at both sites. So if this thickness were to shrink down to essentially 0, but such that we still had 2 reflections, these guys would still be in phase with each other, constructive interference, and hence the condition that the path difference be half a wavelength in the medium N1 is accurate. Had there been phase reversal at only 1, we would have had to revise that. So the thickness that we need is lambda sub 1 over 4, obtained by dividing both sides of this equation by 2. And now I got to find out what lambda 1 is. Let's see, we know that the frequency of the light doesn't change as you go through an interface, and this, for any wave, the speed of the wave is the wavelength times the frequency. And so this is true of the light when it's in vacuum over here, and the speed is the speed of light in vacuum. And I'll call this, I've called this alternately lambda 1 and lambda prime. I want to call it just lambda 1, the wavelength in medium 1. The velocity in medium 1 I'll call V1, So the wave velocity is going to be equal to lambda 1 times the same frequency. And that's the interesting thing, that the frequency of oscillations doesn't change as you pass through this interface, if the light passes through that interface. And just divide this first equation by the second one, because I see what I want is the index of refraction coming out just by dividing that one by that on the left. I get the index of refraction on the left. On the right, the f's cancel, and I get lambda over lambda 1. But again, C over V1 by definition is N1. The ratio of the speed of light in vacuum to the speed of light in that material is by definition the index of refraction. So I've got N1 is equal to the ratio of those wavelengths. Solving for lambda 1, I got lambda 1 is lambda over N1, which in this case is 550 nanometers divided by 1.21. Now, if you look at the numbers up here, two of them are given to 3 sig figs, and then this one's ambiguous. 550 nanometers can be taken as 2 sig figs or 3 sig figs. That 0 may or may not be significant. I'm going to call it significant because the other two are to 3 places. I'll call that 3 sig figs and quote the final answer to 3 sig figs. So lambda 1 is nanometers. Lambda 1 evaluates to 455 nanometers. And if I substitute that into my expression for the thickness, you get T is equal to 455 nanometers divided by 4, which is equal to 114 nanometers. Round it to 3 sig figs. I did try keeping this one to 4. You wind up with the same exact result once you round the final answer down to 3 sig figs. So that's just copying it down. 114 nanometers is the thickness of that coating that you need on the lens to minimize the reflection. You'll see that kind of coating, that thin film coating on binocular lenses, camera lenses, telescope lenses. I've even got it on a pair of my eyeglass lenses. It really does cut down on the reflection. Pretty advantageous for nighttime driving in the case of